Okay, this is the last section, section 6.4, motion in the presence of resistive forces. Let's consider the interaction between a moving object and the medium through which it moves, whether it be a liquid or a gas. The medium exerts a resistive force R on the object moving through it. Some examples are air resistance associated with moving vehicles, air drag, and viscous forces that act on objects moving through liquid, such as the sharks in the water. The magnitude of R, the resistance, depends on the speed of the object, and the direction of R is always opposite the direction of motion of the object's motion relative to the medium. It may or may not be in the direction opposite the object's velocity according to the observer. Example, marble dropped into a bottle of shampoo. The marble moves downward and the resistive force is upward, resisting the falling of the marble. A limp flag hanging on a flagpole. When a breeze begins to blow toward the right, the flag moves toward the right also. The drag force on the flag from moving air is to the right, and the motion of the flag in response to it is to the right. Same direction as the drag force. The air moves to the right with respect to the flag. However, the flag moves to the left relative to the air. The direction of the drag force is opposite the direction of the motion of the flag with respect to the air. Okay, we're going to look at two simplified models. So we're going to assume the resistive force is proportional to the velocity of the moving object. This is valid for objects falling slowly through a liquid and for very small objects, the dust particles moving through the air. The other model is we're going to assume the resistive force is proportional to the square of the speed of the moving object. And this is valid for large objects such as skydivers moving through the air in free fall or trucks driving along the road. Okay, let's look at the model where the resistive force is proportional to the object's velocity. The resistive force is equal to the minus B times V. B is a constant, and the value depends on the properties of the medium and on the shape and dimensions of the object. V, the velocity, is the velocity of the object relative to the medium. And the negative sign, R equals minus BV, the negative sign indicates that R is in the opposite direction to V. We can almost, you think of it as friction. Friction is always opposite the applied force. Now, consider a small sphere of mass m released from the rest in a liquid, as in the figure. We assume that only the forces acting on the sphere are the resistive force and the gravitational force F sub g. We model the sphere as a particle under a net force. We apply Newton's law. We apply Newton's second law to the vertical motion of the sphere, and we choose the downward direction as positive. So the acceleration of the sphere is downward. We solve for A, and we note that A is equal to dv dt. The acceleration is equal to the change in velocity over time. So we end up with a differential equation that contains both V and the derivative of V. It contains both velocity and the derivative of velocity. Note initially when V equals 0, the magnitude of the resistive force is equal to 0, and the acceleration of the force is equal to g. As t increases, as time increases, the magnitude of the resistive force increases and the acceleration decreases. Acceleration is 0 when the magnitude of the resistive forces approaches the sphere's weight. The net force on the sphere is 0. In other words, if the resistive force and the gravitational force are equal, then the speed approaches its terminal velocity vt. Okay, let's look at this figure. To find the terminal speed, we set dv dt equal to 0. Why? Because that is the point at which it's reached its terminal speed. It doesn't mean it's stopped. it means it's reached its terminal speed, and that means no more acceleration. The acceleration is equal to 0. So it can be moving, but the acceleration is 0. It's moving at constant velocity. Okay, if v equals 0, at t equals 0, then the expression is as shown. And the function is plotted in the figure. Okay, here it is. I'm sorry. I should have pressed that one. If v equals 0 at t equals 0, the function is plotted at the right, and this is a curve that we're going to see a few more times. We'll see it when we get to electricity and magnetism. It's the charging of a capacitor and the discharge of an inductor. Now, the symbol E represents the base value, the base of the natural logarithm. It's Euler's number, E equals 2.71828. The time constant, tau equals m divided by b, is the time at which the sphere released from rest at t equals 0 reaches 63.2% of the terminal speed. When t equals tau, the velocity at tau is 0.632 of the terminal velocity. Again, we'll see a similar equation in the next semester when we look at capacitors and inductors. Okay, a small sphere of mass 2 grams is released from rest in a large vessel filled with oil, where it experiences a resistive force proportional to its speed. The sphere reaches a terminal speed of 5 centimeters per second. Determine the time constant tau, and the time at which the sphere reaches 90% of its terminal speed. Okay, we conceptualize this problem as follows. With the help of the figure, we imagine dropping the sphere into the oil and watching it sink to the bottom of the vessel. If you have some thick shampoo in a clear container, drop a marble in it and observe the motion of the marble. We categorize it as follows. We model the sphere as a particle under a net force, with one of the forces being a resistive force that depends on the speed of the sphere. And this model leads to the equation for the terminal speed. For the terminal speed, V terminal equals mg divided by b. Okay, so if V terminal is equal to mg divided by b, then b is equal to mg divided by vt. You should be able to convince yourself of that. So we evaluate the coefficient b, and we solve for tau, where tau is equal to the mass divided by the constant b, and we'll see that the mass times acceleration is vt over mg. So the m's cancel and you get v terminal divided by g. Okay, let's substitute the numerical values. You have 5 centimeters per second, and now notice that they use gravitational acceleration instead of 9.8 meters per second squared. It's 980 centimeters per second squared. It's the same thing, but because we're using 5 centimeters per second, we would have gotten the same thing had we changed it to 0.05 meters per second divided by 9.8 meters per second squared. We get 5.1 times 10 to the minus 3 seconds. Now let's find the time t at which the sphere reaches a speed of 0.9 of terminal velocity by setting v equal to 0.9 vt and solving for t. And here we go. 0.9 times vt equals vt times 1 minus e to the minus t over tau. And we get, the vt's cancel. We get 1 minus e to the minus t over tau equals 0.9. And if we, so we divide, we subtract or actually let's subtract e to the minus t over tau. That makes it positive. And so 1 minus 0.9 leaves us with 0.1. Now let's take the natural logarithm of both sides, and we end up with minus t over tau equals the natural logarithm of 0.1. Minus t over tau equals minus 2.3. And so tau is equal to, t, the time, is equal to 2.3 tau, which is 2.3 times 5.1 times 10 to the minus 3 seconds equals 11.7 times 10 to the minus 3 seconds, which is 11.7 milliseconds. All right. The sphere reaches 90% of its terminal velocity in a very short time. 11.7 milliseconds. You should have also seen this behavior if you perform the activity with the marble and the shampoo. Because of the short time interval required to reach terminal velocity, you may not have noticed the time interval at all. 11.7 milliseconds is pretty short. The marble may have appeared to immediately begin moving through the shampoo at a constant velocity. Okay, let's look at the next model where for objects moving at high speeds through air, airplanes, skydivers, cars, and baseballs, the resistive force is modeled as being proportional to the square of the speed. The magnitude of the resistive force is a function of as follows: R equals 1/2 d rho a times v squared, where d is a dimensionless empirical quantity called the drag coefficient, rho is the density of air, and a is the cross-sectional area of the moving object measured in a plane perpendicular to its velocity. So it would, like if it were falling toward you, it would be only what you see in cross-section. Now the drag coefficient has a value of about 0.5 for spherical objects, but it can have a value as great as 2 for irregularly shaped objects. Let's analyze the motion of a falling object subject to an upward air resistive force. The object of mass m is released from rest, as in the figure. The object experiences two external forces: the downward gravitational force, Fg, which is mg, and the upward resistive force, R. The magnitude of the net force is the sum of the forces equals mg minus 1/2 d rho a v squared. It is downward. That's the positive vertical direction. We can model the object as a particle under a net force. The object has downward acceleration of magnitude g minus d rho a divided by 2m v squared. Let's see. We calculate the terminal speed. I'm sorry. When the gravitational force is balanced by the resistive force, that is the terminal velocity. So the net force on the object is 0. So we set the acceleration is equal to 0 at that point. So we solve the equation above, and if you solve for Vt, you get 2mg. We subtract. We end up with g equals d rho a over 2m v squared. We invert. We end up with 2mg divided by d rho a, and to get the Vt, because right now we have Vt squared, we take the square root of it. So this Vt is equal to the square root of 2mg rho a, where a is the area. Now these are some common terminal speeds for various objects falling through the air. And let's look at a baseball, because we're going to look at that later on. The terminal speed for a baseball, if you look all the way over to the right, is 43 meters per second. A skydiver about 60 meters per second. Now that's going to depend. I mean, if the skydiver is spread eagle with his arms and legs spread out, it's going to be different than if he tucks and heads head first going down, he'll be much faster. Why? Because he's got a smaller cross-sectional area. Um, so a skydiver 60, baseball 43, golf ball 44, a hailstone about 14 meters per second, and a raindrop about 9 meters per second. Okay. Just the table of terminal speeds. Let's look at let's take a quick quiz. A basketball and a 2-inch diameter steel ball having the same mass are dropped through air from rest such that their bottoms are initially at the same height above the ground, on the order of 1 meter or more. Which one strikes the ground first? The steel ball, the basketball, or both strike the ground at the same time? Well, they both have the same mass, but one certainly has a smaller cross-sectional area. The steel ball has a smaller cross-sectional area, so it should go faster. And sure enough, the steel ball does arrive there first. The basketball, having a larger cross-sectional area, will have greater air resistance at any given velocity than the steel ball, which will result in a continuously smaller downward acceleration. Okay, let's look at a problem. Consider a Skysurfer who jumped from a plane with his feet attached firmly to his surfboard, does some tricks, then opens his parachute. Describe the forces acting on him during these maneuvers. Okay, when the surfer first steps out of the plane, he has no vertical velocity. The downward gravitational force causes him and the board to accelerate toward the ground. As their downward speed increases, so does the upward resistive force exerted by the air on the surfer and the board. This upward force reduces their acceleration, and so their speed increases more slowly. Eventually, they are going so fast that the upward resistive force matches the downward gravitational force. Now the net force is zero, and they no longer accelerate, but instead reach their terminal speed, their terminal velocity. At some point after reaching terminal speed, he opens his parachute, resulting in a drastic increase in the upward resistive force. The net force, and therefore the acceleration, is now upward and in the direction opposite the direction of the velocity. The downward velocity, therefore, decreases rapidly, and the resistive force on the parachute also decreases. Eventually, the upward resistive force and the downward gravitational force will balance each other once again, and a smaller terminal speed is reached, permitting a safe landing. Now, contrary to popular belief, the velocity vector of a skydiver never points upward. You may have seen a video in which a skydiver appears to rocket upward once the parachute opens. In fact, what happens is the skydiver slows down, but the person holding the camera continues falling at a high speed. So relatively looking, it has a relative look as the skydiver that opens his parachute of just shooting up, but that's not the case. Now let's look at another example. Let's look at a pitcher that hurls a 0.145 kilogram baseball past a batter at 40.2 meters per second. That's about 90 miles an hour. Find the resistive force acting on the ball at his speed. Now let's go back let's go back to the table and look at the baseball again. It's 43 meters per second. Now we're going to use that data. Okay, let's conceptualize. In this example, the object is now moving horizontally through the air instead of moving vertically under the influence of gravity and the resistive force. The resistive force causes the ball to slow down, and gravity causes its trajectory to curve downward. We simplify the situation by assuming the velocity vector is exactly horizontal at the instant it is traveling at 40.2 meters per second. And we categorize this problem as follows. In general, the ball is a particle under a net force. Because we are considering only one instant of time, however, we are not concerned about acceleration. So the problem involves only finding the value of one of the forces. So let's look at this. We analyze it as follows. To determine the drag coefficient, D, imagine that we drop the baseball and allow it to reach terminal speed. We solve the equation for terminal velocity for D. So the equation for terminal velocity was Vt equals twice the mass, the square root of twice the mass times the gravitational acceleration divided by the drag coefficient times the density of air times the area. So D, if we solve for D, it's equal to, you square both sides, you get VT squared equals 2mg over D rho A. So we switch D and VT squared, you get D is equal to 2mg divided by VT squared over rho times A. Okay. We use this expression for D to find an expression for the magnitude of the resistive force. So the resistive force, we were given the equation equals 1/2 D rho AV squared. So it's equal to 1/2 times D being 2mg VT squared rho A. We substitute that in. Times rho AV squared, we see that the rho A cancel, and so the resistive force is equal to mg times v divided by v terminal velocity times squared. And we substitute the numerical values using the terminal speed of 43 meters per second, which we got from the table above, and we get 1.2 newtons. So the magnitude of the resistive force is similar in magnitude to the weight of the baseball, which is about 1.4 newtons. Therefore, air resistance plays a major role in the motion of the ball, as evidenced by the variety of curveballs, floaters, sinkers, and the like thrown by baseball pitchers. And that ends the chapter. And we'll stop the recording.